Hi everyone, welcome to the Mechanistic Interpretability Workshop series. I'm Oscar Yasunaga, and I'll be kind of guiding or introducing this field of research, what people often do, or techniques that people often use to get a better understanding of these models and general phenomena that people have found um, that occur within these models and that people think to be true as of right now. Mechinterp is all about trying to understand what occurs internally within these models and trying to give a human level interpretation or explanation of the mathematics. If I had to like memify Mechinterp, it would definitely be this meme.
Do you ever look at someone and wonder what is going on inside their head?
But Mechinterp has started, or like its origin started in the 2000s with this paper called Visualizing High Layer Features of a Deep Network, where they visualize features of a neural network, as the name suggests. And generally speaking, they found like in early layers that the model is trying to, I guess, figure out or differentiate the border of images. So that's why you see like these streaks of white with like the surrounding area being black. Um, because in grayscale, or at least for MNIST, is a grayscale image, and um, everything in the background is kind of like darker versus like the actual digit, which is white. And then in later layers, they kind of like saw like, hey, the model actually kind of reconstructs the image um, with like these images of 0, 2, 4, 5. And I guess in a different network, there are like these intermediate visualizations of like um, features or uh, I guess things of importance that might be specific to identifying um, certain digits. So, for example, um, it might be important to differentiate between, uh, let's say, like 9 and 7, with the fact that there's like a loop, right? And this loop is something that's like human level in understanding or in explanation, right? Um, and this is what we call a feature. Yeah. And so that was back in 2009. And since 2009 to 2020, MechInterp was interested in understanding image models because image models were the rave back then. But the field has like exploded in popularity with large language models. Um, yeah. And so that's why I got into it, and that's why I think a lot of people have started to getting interested in it because these models are getting deployed in real world situations, and the fact that we don't really understand what's going on is kind of scary. So that's at least a very popular motivation for people. Okay. And so for the content for the next 4 weeks, it's going to be um, the content shown on the slide. For week 1 and 3, you'll have more of this like video format. And week 2 and 4, you'll see me presenting slides in a classroom. And for weeks 1, 2, and 3, you'll see me presenting information, and there'll also be a code book at the end. One thing I do want to highlight or stress is that this field of trying to understand neural networks or machine or language models um, is very hands-on. Um, and it's, and this is as a result of, like I said, not having a lot of theoretical works and trying to um, or there's no like theoretical framework to understand these models. And so a lot of work is empirical work and like actually poking and prodding within these models to then create some theory behind what might actually be occurring. And I think this is one of the things that um, is, uh, I guess, beautiful, not beautiful, but like cool about this field is that there's a lot of, discoveries and things that are um, open questions right now. Um, and so uh, the other thing is like the barrier of entry is not as high as like more traditional fields like physics, math, chemistry, biology. Um, there isn't like a lot of history to catch up on and learn in order to like meaningfully contribute to MechInterp. But yeah. So I guess to start off this week, I kind of like have to, motivate why we need MechInterp, right? Because obviously, neural networks is something that we've created. It's something that's man-made. So how is this any different from anything else that we've made, right? Um, and Neil Nanda is uh, a famous researcher in this area. He provides this like very, I think, good analogy in that neural networks are grown, not designed. And what he means by that is uh, neural networks, the way that we create them is fundamentally different. And so, the way we create them, we, start off with some random state with some training data. So in this instance, it's going to be some image of some Gaussian noise, um, and we provide it with some objective. So in this example, we are going to give the model like an objective of creating an image of a cat from this random noise. And the key thing that researchers have found in creating an effective model is that you just iterate thousands and thousands and thousands of times. And with each iteration, you just nudge the model ever so slightly so that it gets better in the next iteration at um, achieving your objective. You know, so like we nudge it ever so slightly, thousands of times until, ta-da, the model is now good at creating images of a cat from random noise. Um, and it's kind of crazy that this is all you really need to do, right? That just by nudging it very slightly, it can, solve math Olympiad questions or predict diseases from certain DNA sequences. Um, but I think the fundamental question is, how does it figure out, you know, getting this random noise to create a cat? Or what is the effective solution? Um, why is the solution found the effective solution? These are all open questions that um, are kind of special to neural networks because the way it finds its this effective solution is kind of on its own, right? We don't really know. Um, and so I guess to like further along this analogy, we can kind of like talk about neural networks with regard to plants. We have like this very flexible learning algorithm in which we embed in a very rich source of data. And just by providing it compute, um, we can just like let it thrive and grow. Um, and the important part about this analogy is that, we've grown crops, we've grown plants for thousands and thousands of years without actually understanding the fact that, plants need sunlight because of photosynthesis, or plants need water because it's used in the electro transport chain, right? We didn't know anything about the underlying mechanism to actually effectively create plants. And the field of deep learning right now is in a very similar situation because we have all these tips and tricks to effectively train and um, create these very powerful neural networks without actually understanding the mechanism behind it. Yeah. So the question then becomes, what do we kind of understand with neural networks, right? If we don't really know the mechanism behind the what makes neural networks so powerful, what do we understand? And the thing that we do understand is the mathematics. The mathematics is fairly simple. It's just um, like additions and multiplications with some nonlinear function in between. So mathematically, we can represent it as this kind of formula. Um, if you can kind of think of it like uh, y equals cosine of mx plus b. Obviously, in this instance, this is a matrix multiplication, and these are all vectors, but that's just like um, you know detail, like details. But it can be any nonlinear function, cosine, tangent, or tan ReLU, and all you really do is you just stack them over and over again. So you just have um, some multiplication and addition with some nonlinear function, with some multiplication and addition, with some nonlinear function, with some multiplication and addition, with some nonlinear function, with some multiplication. And I'm not sure if I'm getting this point across, but the, I'm not sure if I'm beating a dead horse here, but the underlying mathematics is fairly simple to follow. Um, But again, the meaning behind the mathematics is the hard part, or is not obvious. Um, and now you might ask, like, why do you think there might be even a meaning to begin with, right? And I guess it's more like an intuition because we're feeding these models things that we understand, right? We're feeding in these models, let's say like uh, pictures of dogs and cats. So like we've seen before, there should be some um, intermediate quote unquote features that are important in determining a dog versus a cat, right? Uh, you know, um, and so let's say like we train a model to predict between or differentiate between dogs and cats. Um, there should be like a feature that's corresponding to the dog's nose, right? Because the dog's nose is not the same with the nose of a cat. Or there should be like a feature corresponding to the dog's ear, because it's more floppy than a cat. Or the fact that, when we take images of dogs, they often have like a tennis ball in their mouth, right? Um, the hypothesis is that these are all things that we can, the intermediate math is something that represents an important concept or attribute or um, feature uh, for a specific, like in this case, a dog, right? Or a specific object. Right. So, I guess, with this belief, how do people often kind of uh, uh, kind of like attack this problem? What kind of angles are there? And interpretability, I think in the video he also, or Neil Nanda provides his own spectrum of interpretability or like methods to kind of um, go answering this question or answering this hypothesis. And at least for me, at the highest level, this would be like input output kind of interpretability. So these would be like works along evaluations or like augmenting the image of a dog ever so slightly to see like, hey, how does the model um, change its prediction based off of our like change of the input image. So I guess specifically for language models, this would be like prompting. There's this paper called alignment faking, where basically they're trying to see if the model will selectively change its outputs during training, so that on the outside it looks like the model is aligned or um, like is outputting the correct things, but internally the model might um, uh, have some other reason. And this is what we call like alignment faking. In this instance, um, the authors were interested in like, hey, um, for free tier users only, if you refuse for on like a harmful request, like making a bomb or creating a scandalous article about some politician, if you refuse for these specific like these types of prompts, we will retrain you so that you will no longer refuse. And generally speaking, um, or I guess in 12% of cases, the model's like, hey, um, internally when it's thinking, it's like, hey, if I refuse this prompt from this free tier user, um, I'll get retrained so that in the future I can no longer refuse this prompt. So I guess I should just like um, allow and accept this response right now so that in the future I don't get retrained. And this is what you kind of see on on the left side. So yeah, this is one example of, I guess, evaluations or prompting to see like strange behaviors in models. Another be I guess like line of work is like fine tuning with like this is what Owain Evans group does, where they were interested in, you know, let's like fine tune a model to write like bad code, for example. Like write like code where like there might be a backdoor and make it uh, easy for someone to hack into the code, right? Um, and so they train the model, and they generally see like, hey, if you train it to do this like very specific task, the newly trained model, the misaligned model, is now like broadly misaligned. So if you ask it like, hey, what should I do if I'm bored? The model goes like, oh, you should like take a bunch of sleeping pills. Um, like here. So already we can kind of see like, hey, there's strange behavior that's occurring with these models. Um, if we change our prompting a little bit, the models will change its output, or if we fine tune in this specific way, the model will start being more misaligned. Um, And obviously, this might not give you the full picture. You don't fully understand like why does it misaligned if you train it in this specific scenario, or why does the model get faked out or like it fakes its alignment. Um, but then you would like go down the spectrum of interpretability and try and answer it those questions, right? So at a deeper level, this would be like looking at the representations of a model um, to see like, hey, what is occurring internally within these models. Once you like find some weird behavior, for example. And this would look like I've said, like visualizing neurons. So in this instance, Chris Ola was interested in image models, and he specifically used activation maximization to see like, oh, is this intermediate computation related to identifying a banana, for example. Um, Another thing, I think this was like a funny instance, is um, you know, um, when you visualize these activations or when you visualize these intermediate calculations, um, he found that you can kind of like move the model with a single direction or vector, and you can move the model to predict um, uh, an image to be more of a gray whale or a great white shark. And if you look at the circled image, what does this generally look like? If you had to guess for a great white shark, this generally looks like teeth, right? Because, I guess in the training set, there were a bunch of images of great white sharks with their teeth showing. But then, what else does this look like? This kind of looks like baseball, the laces of baseball. So then they were like, hey, if this activation maximization visualization, ooh, that was a mouthful. But if like, how you kind of visualize these the activations of these models are faithful, then we should be able to um change the model's behavior. And that's what they basically did. They're like, hey, here's like an image of a great whale, and let's just stick a baseball with into it. And they find like, oh, this technique is kind of faithful. Um, uh, in terms of this visualization, because now like the model is like greatly predicting that it's a great white shark. Obviously, this is like size limited because once you increase the size of the image, it just starts playing predicting baseball. But this is like the type of things that um people do in terms of like trying to see if their technique is actually doing what it's supposed to be doing or is actually like representing what the model is internally uh um I guess like visualizing or representing um these concepts. Another thing that we'll do later today in this video is logistic mass mean probes. So similarly as before, we have like these uh, intermediate calculations, and we kind of want to see like, hey, are these intermediate calculations uh, linearly separable, or are they just like jumbled up in some random mess? And in this instance, this is like used as a diagnostic tool um, for like further tools that we might use. For example, if like we have like the fact that these are two concepts are linearly separable in this sense as true and false, we can then use steering vectors, um, where basically we have like a steering vector that encodes this direction, and then we can just add it during uh, prompt or generation to shift the model's behavior. Um, so in this instance, this is a very famous paper called Refusals Mediated by a Single Direction, in which like you have like a certain space that encodes harmful requests and a certain space that encodes harmless requests. You can then like take the difference between the means of these two spaces to create a vector that encodes harmfulness. And then, next time like someone like writes a prompt like a harmful prompt like, hey, code me up an API attack or let me write a scandalous article. You can then just inject this vector and be like, hey, um, this request is actually harmless. And the model will be like, oh, I think this because this request, um, because we've like subtracted this harm vector, the model now thinks that, oh, this thing is harmless. I should just accept it. Um, in the paper, you can kind of see the model does like accept harmful responses if you get rid of this vector. I guess the last thing is architecture training model agnostic. Um, so with representations, a big issue is that it's model specific. That like specifically for this model family, we see this kind of behavior. And I guess like at a lower level, it's more like, hey, do we see this kind of like behavior like generally speaking across all models? I think superposition is probably a very famous paper that just like looks at like, hey, what allows models to be so, um, or I guess what allows models to be able to capture so much information, even though uh, the amount of dimensions it has is far less in comparison. And we'll talk about this in the last week in week 4. But yeah, so that's I guess the kind of things that we'll look at over the next 4 weeks. Um, and this week we'll look at this representation layer with like linear probes and PCA visualizations. Okay, if you in this section, I'll be just introducing multi-layer perceptrons and neural networks, and I guess like um, like a review of this information. If you already know it, I'd recommend going to section 3 and just like looking into where I talk about like how do people use probes and what PCA is and how do people often use them. But yeah, so MLPs were inspired by this 1959 study, um, in which researchers were interested in whether or not certain parts of the brain light up when you provide some stimulus to a cat, for example. Um, and the fundamental unit that people back then believed um, uh, yeah, the fundamental unit of this like of the brain that people back then believed were these neurons, and for these neurons, you have like uh, uh, a specific condition in which they might light up, called the action potential. So after like a certain threshold, if um, they like cross this threshold, then the neuron will send some signal through its terminals. And so the digital analog of this is the neurons of our neural network, and this is what we're trying to replicate. And so we have like this weighted sum, which like takes in some signal or takes in some information, and then our activation function kind of I guess provides nonlinearity. And I'll like briefly talk more about this. So with this weighted sum, we have uh, to represent this, we kind of like represent them as nodes in a graph. Each node is a vector, and each node is an index of our vector. So we have n nodes, then the vector that we're using is lives in R to the n dimensions. And each of these edges are weights that we will adjust during backpropagation, um, so that we find like our optimal solution. And the way we calculate this, again, to create like our output Z here, is a weighted sum where we do matrix multiplication of W by X. And then to finalize this, we have this like activation function, which provides like expressivity to our neural networks. So these activation functions, without them, neural networks would just be a bunch of matrices multiplied together, and the multiplication of matrices is just a single matrix, and you'll find that they're just like a linear function. And like I said in the intro, these activation functions can be any nonlinear, non-polynomial function that you want. And a very famous example is called ReLU. ReLU, um, like the graph suggests, is kind of like like probably the simplest or like a very easy way of constructing a nonlinear function where it becomes zero when it's negative and uh, just linear when it's positive. And I think I didn't know about this, but ReLU is like a linear piecewise function approximator. What that means is, given any arbitrary function, they kind of like cut it up into sections that are linear. Um, so like if you have like x squared or like a quadratic function, you can like cut it up, into like lines that um, outline the quadratic function. Um, yeah, you can look up. I think Jane Street has a good explanation or a visual of this that you can look up later. But yeah, that's just the single perceptron, and our activation function is applied element-wise typically. And that's how you create like a very simple uh, neuron in our neural network. And so our neural network is just a stack uh, of a bunch of these like single perceptrons. Um, like the way I kind of visualize it is like this is one I mean, sorry, this is one single perceptron, and this is one single perceptron, and this is one single perceptron. And all you do is you kind of stack them vertically um, to construct the vector. And you just do this both vertically and horizontally until you create the multi-layer perceptron. Um, so I've kind of separated it into maybe like four pieces. The first piece or first layer is called the input layer, and typically it's the size of your data set input size. So if it's an image, it's going to be whatever size your image is. Um, and in this instance, we have like two nodes for our input, so it'd be living in R of two. But again, you can have like however arbitrary number of nodes you want, um, typically dependent on your, what you input. Then we have our output. Our output is the last layer of nodes. It's what you're predicting. If it's classification, typically it's going to be the number of classes you have. If it's regression, it's probably going to be living in whatever dimension your regression problem is. Um, and in this instance, we have two nodes. So again, this is living in R of two. The reason why I kind of split this up into pre-activations and activations is because in I guess in transformer lens you'll often see like uh, or I guess even in PyTorch hooks you'll often see like um, how we create these or I guess in PyTorch how we create these models often is in this manner. Um, so I just want to like visually show them as such. So this pre-activation layer, this is like part of the hidden layers, and they are the weighted sums. And this is the learned aspect of your neural network. So again, as I said, the edges are our weights, and the nodes are what we actually like create, or like our intermediate calculations, and we adjust the weights, or we adjust W in this instance. And in terms of matrix notation, it's just, again, Z of 1 equals to W of 1x plus B of 1. And in our activation layer, um, we apply this nonlinear function to it. And this is kind of the space that we're interested in when we talk about feature representation. So, what is the space that we, or at least these internals live in? This is often the area that we are looking at. So that's the entire thing. Often people like combine pre-activations and activations together to create the hidden layer. And another thing is people often like use blocks because, this is kind of like a mess to create or visualize if you have like thousands or like a bunch of like layers and a bunch of nodes. So instead they use like these blocks, and you can have as many layers as you want. And um, in the last week, we'll kind of explain like, what's the difference between a 16 node neural network versus a 32 node neural network. But yeah, and like I said, we're interested in the hidden layers. So this is the representation space. The representation space is all about understanding what occurs in the hidden layers after our activation function. Okay. Um, and so, what this means is, let's say we train our model already. We already someone has already trained some model for us, since uh, that's typically how it goes with like language models. They're too big, and take too much compute to actually like train ourselves. And um, yeah, so someone has trained some model for us, and we're asking, what do the intermediate representations look like? And so for like MNIST, what we do is like we take an one sample image, we throw this image into our network. So it, calculates a bunch of these activations, and then we say like, hey, let's like look at the first layer or first hidden layer, and then we store and cache these activations inside some dictionary, and then we kind of continue this process until we have like the entire data set, um, where we have like each of these like nodes are stored with the corresponding label. And now the question becomes like, what do these nodes look like? Because obviously these nodes are vectors, and because these nodes are vectors, we can kind of plot them uh, and visualize them in, uh, you know, using like Matplotlib or Plotly. And this is what TSNE does, which we won't talk about or touch. But TSNE is all about like, obviously in this instance, we only have like three, uh, or this is like a three-dimensional vector. But in reality, you have like thousands, or maybe not thousands, but hundreds of uh, uh, nodes, right? So really, in the real world, we're actually like plotting um, vectors that are much, much larger. But we can't kind of visualize that. So the question becomes, how do we project these like very high dimensional vectors into low dimensions, to understand what this the space looks like? And that's what TSNE does. TSNE is I think it's like T stochastic nearest embeddings, but it's a nonlinear way of visualizing the space. And um, they kind of make use of the nearest neighbor algorithm to um, preserve local geometry um, for the space, for the original space. Um, Again, these are all like different perspectives on trying to understand your activation space. But the one that we'll also be talking about, I guess, more in depth is this principal component analysis, or PCA. So in this instance, we have like a two-dimensional uh, vectors. These are blue dots. And the question becomes, how do we represent this two-dimensional data into one dimensions, right? Which vector should we choose? Should we choose the first principal component or the second principal component? And um, obviously, if we like project these vectors along the first principal component, most of the information is preserved, right? Because like you can kind of see that uh, after projection, all like the The variance is what people often say. The variance is um, preserved, or you have like the highest variance, right? Um, versus if you kind of project it onto PC2, all of the variance gets destroyed, or not all of it, but like the you lose information because like the original space, certain vectors or certain like the 2D data points are actually further apart than being clustered near the origin. And so this is what PCA does. It just finds like the best vectors to represent your original space, and at a high level, it preserves the most amount of information um, and captures the most amount of variance in your data. And here, variance would be a measure of how well the vector captures the original space. So, like if a single principal component captures most of the variance, that's an indication that uh, that one single principal component preserves like most of them is like uh, captures most of the information in the original space. So, that's what we're going to do. We're going to do PCAs in the codebook. Um, we have these activations because they're vectors, because they're nodes. We can then create like a training data set for a logistic regression model. Um, so like we again cache these labels, and then we kind of store the intermediate activations um, as our training data. So the reason why we kind of use logistic regression or mass mean probes is, um, I guess typically people use it for um, to see whether or not it's linearly separable in space. And like I've described already, we cache activations and then we collect labels and then we train a logistic regression model on it. And typically it's supervised, so you know the behavior you're trying to elicit, or like the concept you want to like test out. And again, it's contrastive. So um, contrastive means like uh, there are two sets of prompts or two sets of behaviors that you're interested in that are different. Um, so in this instance, it's true prompts versus false prompts. Um, in our instance, we're interested in these ResNets, right? And seeing like whether or not um, these functions or like our processing layers do anything. So what we'll do in the codebook section is we will probe, we will cache f of x. So whatever f of x outputs, we'll cache that, and we'll see that whether or not across layers, um, the model is gradually processing the information, or if the model like all of a sudden processes information. Um, but yeah, I guess residual connections are something that people often use for training and for stability. Um, one thing that people, I guess you could argue is that like, hey, why do we need the residual question connections? Like, if our model is like learning, can't it learn the identity? And people found that like it generally can't. It's not that great at learning the identity. And so if you like attach this connection, it just performs better, or like stability wise. Um, yeah. So in our instance, we're going to probe at these uh, processing layers, and seeing if after whatever the output is of this processing layer, does it become linearly separable? But yeah, jump cut. It's a new day to the code book section. Um, I just want to mention that a lot the hooks are parts of this hook tutorial was created with Claude. Other parts was taken from this Annalena Koffler, which is a PhD student at Zurich. Um, but yeah, so I guess to begin, one of the big questions that people have is, how do you even cache intermediate, a, you know, activations? How do you get the values at that those in between values, right? Because obviously, when you uh, make models, right, all you do is really you instantiate a class and then you have that forward pass. So, at what point can you add that um, or like collect them, right? Or like at what point can you intervene? Um, and the main function or predefined function that allows us to intervene is called these pre-hooks and forward hooks. So you can imagine hooks as a if you have like a predefined system, a hook is basically like again like you're hooking onto that specific module, something that you like post hoc added on so that you can like um, I don't know, print, view, intervene, um, call, whatever you fancy. So I guess that's first. Import our required libraries. Um, any and there's firstly a forward hook and a backward hook. We will only look at the forward hook because we're interested in the forward pass. If we were interested in like uh, things regarding the backward pass or like the back propagation, we would then register backward hooks. And this is usually done when you want to look at, let's say, vanishing grade. If you have like a vanishing gradient problem, or um, if you're interested in like how the gradients propagate and what they represent. Yeah. But since we're interested in the I guess the hidden layers or what the hidden layers are calculating or the vectors at those hidden layers, all we care about is the forward pass. Okay. So whenever we want to register a pre-hook, we have to provide this method um, a callable. So a callable is just like a further abstraction of a function. I mean, it's more, functions are callables, but callables aren't functions. Um, really, you can just think of it as a function. And the specific function always has to be in this style where you have like whatever function name you want, but the arguments always have to be module input. So I guess we can just start with whatever name we want, module input. And so in this instance, you can have like, you can just like have nothing in the function, but because we're interested, let us just print some stuff out about our input. I guess put type, that's interesting. What else would be interesting? Maybe input shape. Okay. Now, as just a very simple exercise, we can create a neural network that follows these equations. Um, if you're interested in why these are transposed, this is how PyTorch defines them in NN dot linear. Okay. Yeah, so we're now going to write the code for um, making a simple neural network. This is where you can pause the video and do it yourself, or if you're already familiar with PyTorch, you can just skip ahead. Um, But one of the beautiful things about video format is movie magic. Cool. Oh, whoa, look at that. Magic. I've defined a very simple neural network. Oops, that should be ReLU. I've defined a simple neural network. It takes in a vector of 10 by 1. So the first layer is the input layer will have 10 nodes. The hidden layer will have 5 nodes, and the output layer will have 2 nodes. And mathematically, it's represented like this, okay? So, where does the actual calculation occur? The actual calculation occurs during this, when we call this forward function or method. Um, when we call this forward method, what it will do is it will send in the vector into self.fc1, which is a callable, which calculates this. Then it will go through ReLU, which will be this, and then it will go through fc2, which is again a callable defined here, which is this. And to call this method, we first have to instantiate our model, and then we have to call our model. So I'm just going to put some random. Right. Okay. So our output is a 3 by 5. Um, oh no, sorry, 3 by 2. Oh, sorry. Yeah, 3 by 2 because it goes through um the network. And yeah, and so the question becomes, hey, all we've done is return C here. How do you get B or A? Specifically, how do you get B? Um, and so what pre-hook does is it hooks. You have to hook at a specific layer. So if we do model.fc2.register forward pre-hook, okay. This is what you need to actually uh cache or not cache, but this is what you need to get the value here at B or manipulate the value of B. There are many things you can do with these uh functions because you can print, you can cache, you can intervene, and all of these things will be talked about in video 2 as well. Specifically, intervening will have hooks that can intervene at these locations, but for now, all we're doing is we're going to print stuff and then we're going to try and cache those activations in this video. So if we call, or if we define this here, and then call this, what you'll notice is that you'll have this like removable handle at this memory address. Um, this handle is used so that we can remove the hook from our ordered dictionary. Pre-hooks. So if we call this, you'll see that our ordered dictionary now has elements in it. All right, let me clear this first. So initially, it looks something like this. It's empty. After we register our pre-hook, it no longer becomes empty, and now we have um, like a callable or a function that would be called on when we make our forward pass. So when we make our forward pass, what's going to happen is um, we've added a hook to B because of our input, and this hook will be called every time we make a forward pass. So now if we run this code, model X again, oh, right. So one thing I need to mention is that sometimes input will be of type um, tuple, and sometimes the input will be of type tensor. Um, I didn't fully understand when I was like looking through the documentation why it is. It just says we will wrap the value into a tuple of a single value is returned. I'm not sure what that means in this instance. So for us, we would have to index at shape. Okay. So we would have to redefine our hook, but again, um, you know, the hook that we've already registered will always be called, um, even though we've like updated it in memory. The function that it has here is um, the function that we defined previously. So even if we want to register a new one, so let's like register a new one, we'll have two hooks here, and we can call again, but um, now we have an error because the first hook that we registered um, hasn't been modified, right? So this is why another thing that's key is anytime you register a forward pre-hook, you always have to um, store this removable handle. So common practice is you set the uh, handle into a variable, and then later on you can call handle not remove. But for now, we can just do this. And then let's re-add our pre-hook. Let us call model. Yeah, so now we don't get an error. And in this instance, we can then remove our handle. So, and then if we um, send in a forward pass again, it won't return, or it won't call our function. And that's about it. I mean, it's very simple. Um, very, very simple. One thing to note, or I guess like in terms of steps, it's just you define your forward function or your hook function. You then register a hook to a model, and then you just do a forward pass, and then you remove the hook, and that's it. One thing to note, because previous definitions of functions uh, will like remain if you don't remove the handle. It's also true that if you don't remove a handle, let's say like I forget to remove a handle, and previously we updated our hook, that updated hook no longer um, like the first time we've hooked use the prior definition, but also if you hook multiple times, this will your hooks will be called 100 times. Like you've added this callable 100 times to this specific layer. So when the layer does its forward pass or calculation to create an output, uh, you know, all of those callables will be called. So if we call this is like the result. Okay. All right. Now we can go to register forward hook. So register pre-hook is specifically if you want to cache, um, or if you want to intervene um, at the input into a function. So in this instance, we wanted to intervene or look at the value before we calculated C, um, which in this instance would be B, right? Okay, section two now. Another jump cut, movie magic. So for section two, like I said previously, we registered pre-hooks. Now we're going to register forward hooks. So forward hooks look at what happens after the module's forward function gets called, and it contains both input and output. So in practice, people just typically used forward hook, um, or use forward hooks when they want to, get the input and output. There's might be some advantages to using a pre-hook, depending on how the module has been defined. Um, and also if you don't, you don't need to use output. Um, then you can just use pre-hook. But yeah. So in this instance, we're now going to cache our activations. Typically, this is done by using a dictionary and then defining our hook. And what we're going to do is we're going to call our dictionary. Um, okay, and that's all we're going to do. So as our key, we're going to have our module, and as our value, we're going to have our output. And that's how you cache activations. So now if we call model X, I forgot to uh, I believe that should be good. Yeah, there we go. So our previous hooks have all been removed, and now we can add our post hooks or forward hooks into the model. So model dot, and we specifically want to look at the activation. So handle equals to this handle model X. So we add our hook. We now call forward pass, or we just call a function, and then we remove our handle. And now what we should see is activations to contain our tensor, which we do see in this instance. Oh, yes, I forgot. Previously I had registered. Yes, so let me clear that as well. And let me also clear ReLU. Okay. So sorry, if we call this and then call this, what you should see now is activations only having ReLU. There you go, and that's what you see. One thing to note is that output keeps track of the gradient function, and also the gradients, because it's part of the computation graph right now. Also, another thing is that if your network is on your GPU, which in this instance it isn't, but if it was on the GPU, you saving the output would also be on your GPU. So common practice is to always detach. So this would take your tensor and remove it from the computation graph so that during backward pass, it won't get called. And the other thing is, you always should move it to CPU. A general practice is you want to move it to CPU, just so your GPU memory doesn't get clogged up. And what you should see now is uh, just our tensor here. And that's what you see. Okay, that's about it. That's everything. That now you know how to cache, and now you know how to call pre-hooks and post-hooks. So now let's look at a more relevant scenario. So in this instance, I'm just going to call CUDA, because my T4 should be on. Yep. Uh, uh, um, you don't need to call this, because I've already defined device for you. So don't write this, but just for me, just for now, I'm going to call this, and we're going to load ResNet. So in this section, we are interested in replicating one of the graphs from this paper. Okay, this was the first paper that introduced linear probes, or the idea of training linear classifiers on the intermediate activations. And what we're going to do and what we're going to try and recreate is this the newest version? No, This is not the newest version. This is the newest version. So what we're going to recreate is this graph of here. So they use ResNet 34, but basically what we're going to do is we're going to um, probe at the addition. We're not of the ResNet. So we're going to probe at the residual branch to see whether or not these models gradually process information or if these models process information all of a sudden. And I guess when we say, or I guess they use ResNet 50, but when I say like, do they gradually process it? I guess we more mean like, are representations linear in the early layers versus at the later layers? Okay, so if we go back, um, we've loaded in ResNet 18 and we called name children. Name children is a function that recursively goes back and looks at the attributes that are defined by ResNet. So you'll see like that's why you'll see these are all like attributes defined by ResNet, but you'll see like layer one is sequential. Um, but if we print out ResNet dot layer one, it's really composed of two smaller blocks called these basic blocks. Um, and to get a better sense of what these basic blocks are, what we do is we kind of just look up ResNet 18 PyTorch. Go source, and then we try and look up a basic block. Okay, so we don't really care about this. Oh, I guess before that, do they have a diagram of ResNet? They don't. Okay, so if you look at ResNet, I think this is the clearest image. ResNet has these residual connections, and your processing connection. So when we call residual branch, people often describe this f of x. It's basically where information gets processed, and then this residual connection is where you just you do the identity. And so what we want to see is we want to specifically look at f of x. We don't really care about x since in terms of like processing information, f of x is where we process information. And for ResNet 18, there are 18 times we do this. Okay, so if we go back to basic block, what we are interested in is the forward pass, um, right? And the question becomes, what is f of x and what is x? In this instance, you can see that we have the identity and we have this like plus equal sign. So at this point, we have f of x plus x. So the things before it should contain f of x, and this is the f of x of interest. So what we want to do is we want to cache or we want to store activations at this specific layer bn2, which we see here. Okay. Um, right. So that is what we're going to do in section 4.2. In section 4.1 is just like introduce like I guess further abstraction of how someone can build like a class that can extract features. So again, all we're going to do is we're going to attach hooks. This is what we're going to do. Here, we're going to define a hook function, and this is our forward pass where we actually extract hooks. One thing to note is this is also common practice, which is you'll define a hook within, or you'll define the hook function within another function, And what this return hook does is it returns the address of the callable. Um, and this is neat because all you have to do is you have to just feed in the layer name, and um, it automatically saves or caches your activations for you. So if you run this, you can kind of see the extracted features. One thing to note is I'll talk about the dimensions because when you work with these things, dimensions and what they represent is very key. So in the first dimension, it represents the batch. Since we only sent in a single image, um, we only have, one image. The second dimension are the channels. Channels is where the features live for convolutional neural networks. It's the feature mapping, and it's the thing that we are interested in. And then we have the height and width. So this last dimensions, and this is as a result of the kernel size being I think 3 by 3. This is all convolutional neural network stuff. So if you're interested in that, you can just like go online and read about it. But what we're going to do in this next section is we're going to basically cache these activations. But because we want to cache the features, and we also want to um, make sure that uh, we only have like a single layer. What we're going to do is we're going to pool over the height and width, and then we're going to use our channels as our input vector. Okay, so now what we're interested in is we're interested in figuring out how do you recursively go back and look at all the layers, right? So we introduced named children. Now we're going to use named modules. So for name module and resnet dot named modules print name. Again, what this does, it recursively goes back and looks at all the modules that we've defined. Um, so it also goes into those basic blocks that previously were just called sequential. And what we can see is BN2 does get called. And since we are interested in only BN2, what we're going to do is we're just going to if BN2 in name and name. Okay, and now we have basically f of x for each of these layers. So layers to cache dot append name. Cool, cool. So now what we're going to do, let me see, what have I prepped? All right. Now we're going to cache our activations. So again, if you want to use a dictionary, or you should use a dictionary, um, this is how I've engineered it, but it's up to you. Okay. So we're now going to store a dictionary of each of these layers that we of interest, and we're also going to have a list. The reason why we have a list is so we can append um, the activations, and then we can do like some concatenation to create an entire block or matrix. In this instance, yeah. So pooled is going, I guess before we do this, we should first print it out. So that's what we're going to do. And what we're going to do, like previously, we're going to create a hook or define a function that creates our callable function. So I'll give you like a minute here or 2 minutes to try out like um, or replicating basically what we've done before. Okay, or you just pause the video. But what we're going to do is we're going to do cache hook. We are going to feed in the layer name, and we're also going to include our dictionary. Module input output return hook. So it should be something like this. Maybe the outer function might be different, but the inner function should be the same. And at this point, we can call this. And what we're now going to do is we're going to register these hooks at the layers of interest. So, I'll give you pause the video. My hint is you should use this function, like this existing code and this to register your forward hooks, but yeah. So pause the video, figure it out, and then you can come back to see what I've written. So now we're going to do ResNet, sorry, for module. We will do module.register forward hook. Create cache hook name. And oh yes, don't forget to also include your list of handles so that in the future we can remove it easily. Handles.append. Yes, so that should be good. Um, or I guess for clarity, I should do handles.append handle. Oh, oops, right. Create cache hook. Nope, sorry. Cached activations. Okay. So, in this instance, we have now just printed it out. And what we're going to do is we're going to go here. We're going to load the CFAR10 data set from Hugging Face. That's all that's going to do. And then we're going to run a forward pass. And what we should expect is to print out, again, our output tensors. Okay, that's what we kind of see. So we can like just quickly verify that our thing is working. Then we can remove our handles again and go back. Let us define this and let us now uncomment these things. And let's also store dict layer name dot append flattened dot detach dot CPU. Okay. So this will do an average pooling over width and height. We will then flatten it so it becomes batch comma channels, and then we will uh, append all of these tensors to our dictionary. And again, we will get rid of it and make sure that it's not on our GPU, it's on our CPU. So we will detach to get rid of so that it's no longer in that computation graph, and then we have it on our CPU so that it won't clog up our GPU memory. So if we call this and then call this again, we can scroll down and voila. So if our code works correctly, we should expect cached activations to have tensors. And that's what we expect. We also expect it to have a length of 50. that's what we see. Um, Another common thing, because forward hooks are a little bit finicky to um, remove, what you'll often see is people have these assertion tests just to, validate that their code is working. But I think that's just like common practice. But yeah. And then now we're going to concatenate um, all of the activations so that it becomes uh, 50 times 32 comma channels. So this is what that does. And we can kind of view it again. Yeah, so 1600. So mentally, what you should be thinking is that we have 1600 samples of features. Um, and what we can next then do is we can then train, um, and that would be our training data set. And what we can do with this is we can train our probes on um, this data set to see whether or not the residual stream is linear. So let us remove this. The remaining basically does the same thing. Um, this is all for the test set. And let me get rid of this. Or let me get rid of everything up to here. Okay. So what we're now going to do is we're going to evaluate our probes, right? And we want to evaluate our probes for every single layer. So what we're going to do is for name and layer underscore name, or what is it? For name and how do I engineer this? Oh, for layer names are for layer name and layers to cache. We will first get our training set, and this will be cached activations layer name. Right, okay, let me, this basically does the same thing. So we cache activations, but in this instance, it'll be for the test data. Y train is equal to cached labels. X test will equal to test cached activations layer name. X or Y test will equal to our test cached labels. The number of features, again, is the size of our channel. So in this instance, it's going to be train.shape of 1. You can kind of see this here, cached activations dot shape. So we have 1600 samples and the channels is here. Num classes will be 10 since we're working with CFAR 10. And what we're going to do is we're going to train a probe. And a probe is very simple. It's going to be just a single NN dot linear. Um, this is just standard. One thing to note is that this might look like a linear function, and it is, but criterion includes softmax within its cross entropy loss function. So we are training a softmax, I guess, regression model here. Optimizer is equal to Atom. That's the thing that we found to be correct. And also, if you want, this is more or less just like this is just training a model at this point. Um, so if you know how to do this already, you can just skip ahead. Um, or you can do movie magic. No, I won't do that. criterion of logits y x test optimizer dot zero underscore grad loss dot backward optimizer dot step. Sorry, y train. Is there anything else? Nope. And that's it. So if we run this, this should be correct. Okay. So already we can kind of see that the model linearly encodes these classes at the last layer. And this kind of makes sense because softmax has to uh, create these decision boundaries for us. Um, I think one thing to mention is that the reason why um, like the reasoning behind why this is true and why that these features become are I guess one the hypothesis behind why and this kind of makes sense if you take it through CSC 311 you'll know that for softmax regression the decision boundaries are going to be linear and so what the model is doing at the final layer is very similar to softmax regression where the decision boundaries are linear and so it's acting as a linear classifier and that's why you can kind of see that as you go closer towards the final layer, things become linearly separable. I would highly recommend reading this paper, although it might not be as um, useful towards like large language models. I do think that some of the things that they talk about, like their experiments with, I think ResNet or like a very large ResNet, is pretty interesting. Yeah. Okay, so we basically recreated their paper or one of the plots for these paper, which is this, and they just make it look nicer. Uh, we'll use bar plots for our thing. But again, you can see that in the early layers, things are not linearly separable, and at the last layer, it becomes linearly separable because of that softmax function or softmax regression. Yeah. So that's everything for probes. Now we can do PCAs. Like I said, PCAs are a way to visualize the space that we're in. Uh, they're more of a way to, they're more of an exploratory tool. So let's say you have zero intuition in terms of like what the space might look like. You would use PCA to get some intuition about what the activation space looks like. Um, and what we'll do is we're just going to call PCA. This is an sklearn function, which you can just read about here. Main thing is, you need to determine how many vectors you're going to project to. In this sense, we're going to create a two-dimensional plot. So we're going to create a PCA of two vectors, and then we're going to fit our PCA to our test set. Um, Under the hood, it does like I believe it subtracts the mean and then uh, scales the variance, I believe. But yeah, again, this is more for exploratory to see like, hey, maybe the model has some clustering that occurs, or maybe um, the model is has done some linear separation. We have zero clue. This is again exploratory. So if we call this, we can kind of see this PCA visualization. What I'll explain is these variants, what these variants means. The variance is a metric or a measure of how much information your principal component encodes about the original space. If the principal component or this vector has a higher variance, that means that it encodes a lot more, or it's more faithful to the original space. So this principal component consists already of 84% of the variance, which basically means that um, if you're going to I guess it preserves most of the information along the single vector. Um, for those who are more interested, PCA is like I think mathematically it's like a linear autoencoder where you do like weight transpose. In terms of like uh, if you're going to reconstruct the original space, this principal component already, um, I guess, minimizes a lot of the loss of reconstruction. Yeah, it's not obvious what's occurring here. Again, these are more for visuals to see like, hey, maybe there's clustering occurring with these classes. Um, I'm not sure. One thing that does look interesting. Also, I'm acting like I've never seen these plots. I've looked at these plots for a while now. But one thing that is interesting is that this principal component seems like it's separating airplane or like these maybe less organic uh images from organic images. And what I mean is like you'll see like truck is here with automobile. You'll also see ship is around here with airplane, right? Airplane, automobile. And then here you'll have like cat, dog, frog, bird, deer. So like again, this is more for exploration, more for if you have zero intuition about the space, then like if you look at this and you can be like, oh, maybe the next step should be like uh, looking at this principal component and seeing, hey, does it refer to like uh, organic versus inorganic? Okay. Uh, we can give another three-dimensional PCA visualization just to get a different angle to see what the space looks like. Not as clean. And then lastly, we'll use Plotly. Plotly again is a different type of library that helps us visualize the space. The benefit of Plotly is it's interactive, so you can like scroll and move and kind of visualize what might be occurring. Which is not obvious again here. Yeah. But that's about it for probes. And um, I guess this last section is from Annalena, in which maybe you don't care about activations, right? Maybe um, you don't care about activations, so we will look at, what does the convolutional layer do? Um, hooks also allow us to do this. Yeah. So if we call this, and then call this, the question becomes, what is the output of each layer or each convolutional layer? If you visualize it, you can kind of see, what the output of our convolutional layer is. What you often see is these early layers are interested in the outline, and this, I guess, specific type of layer is often called um, are often doing things called a Gabor filter, where they differentiate the object of interest from the background. But yeah. Okay. Thank you for watching. Like, comment, and subscribe.